Welcome to classes by Inspire Physics. Today we have another problem in electromagnetic induction. See, the question is, the given figure shows a metal rod PQ resting on a smooth rail AB, both in horizontal plane. Means the metal rod and the rails are in horizontal plane in a uniform magnetic field which acts vertically downward. So a magnetic field is acting vertically downward, two rails in horizontal plane, a metal rod PQ also placed in horizontal plane. This rod is moving in this direction. Horizontally it moves on the rails. But magnetic field is vertically down. So when the rail moves, it cut the magnetic flux. Okay. A galvanometer G connects the rails through a switch. So across the ends of the rail there is a galvanometer connected like this. One end is connected to switch. One end of the switch, other end is connected to galvanometer and connected to the switch. Length of the rod is 15 centimeter. Magnetic field is 0.50 Tesla. Resistance of the closed loop containing rod. For the closed loop we have resistance 9 milliohm. So this is a situation. So we have magnetic field in vertical downward direction. See, I'll give you an example. See, we have the magnetic field like this, and this is the conductor PQ. This moves in this direction. On the rail it is moving. Say it is moving like this. But we have magnetic field vertically down. So what happens? It will cut the magnetic field. See, it will cut, when it moves, it will cut the magnetic field. Magnetic field exists in this region. So when the conductor moves, it cut the magnetic flux. Magnetic field is vertically downward. Conductor is moving horizontally. Okay. So conductor is placed horizontally. Now, first question we have. Suppose K is open. The key is open. Key is open. And the rod is moved with a speed of 12 centimeter per second. Rod moves at a speed of 12 centimeter per second in this direction. Give the polarity and magnitude of induced EMF. We need to find the polarity and magnitude of induced EMF. That we need to find out. Okay. How will you find polarity? See, magnetic field is vertically down. And conductor is moving in this direction. Okay. In this direction, conductor is moving. So we need to apply Fleming's right hand rule. In right hand rule, the thumb indicates direction of movement. Forefinger indicates direction of magnetic field. See, magnetic field, forefinger indicating downward. Then thumb is indicating what? Thumb is indicating in direction of the movement of conductor to this direction, thumb. Then the middle finger is indicating like this. It is indicating in that direction. So in this direction. Downward magnetic field. Then this is the direction of movement of conductor, and this is a direction. See, figure in this direction. Say if this is a conductor, we can see that induced current in this direction. So this is the direction. Okay. So in this direction, induced current means from Q to P. So induced current is from Q to P. I'll draw the conductor. If we have the conductor like this, both ends of the conductor. This is Q and this is P. So induced current from Q to P. I can mark the induced current from Q to P. Then electrons in conductor move in opposite direction. We can say the electron move like this. Electrons move from in this direction. That is P to Q. Electrons move. When electrons move in this direction, the side P will lose electrons. So since it loses electron, it will be positively charged. And this end will be negatively charged. Okay, so this end develops a net positive charge, here net negative charge. So here is an electric field existing in this direction. I can say across the conductor there is an electric field in this direction. Since there is electric field in this direction, electrons moving in this direction. Electrons are moving in this direction. Okay, electric field in this direction. What happens is these electrons will experience a force. Okay, electrons experience a force. Electrons are moving in this direction. Negatively charged particle, it experiences a force against the electric field. So the electrons experience a force in the electric field, and that force is given by, we know the equation of force. Force is equal to minus E into E. E is the charge of electron, E is the electric field. It is against minus. Electric field in this direction, it will experience force in upward direction, that is Q to P. Okay, so I can say the direction is from Q to P. So the electrons experience a force in a direction Q to P. So what's our question? We need to find the polarity of magnet-induced EMF. Polarity and magnitude. What's the magnet-induced EMF? Induced EMF is from, I'll give the direction. Polarity is from Q to P, I can say. Induced EMF is from, induced current or induced EMF is from Q to P. Q to P we have induced EMF. Okay. Q to P, this is direction induced current or induced EMF. Q to P. The end P is positively charged, end Q is negatively charged. Electrons moving in this direction. So there's a net plus charge here, minus charge here. There's an electric field in this direction. Electrons moving in the electric field in the same direction of electric field. So it experiences a force. The electrons will experience a force in the upward direction Q to P. So electron experiences a force in Q to P direction. What's the direction induced EMF from Q to P? Now what's the magnitude? We need to find magnitude induced. How will we find magnitude? We have the equation of induced EMF E is equal to BLV. BLV. What is B? B is 0.5. So B is 0.5. Length of the conductor is 15 centimeter, 15 into 10 raised to minus 2. And what's the velocity? Velocity of the conductor is 12 centimeter per second. 12 into 10 raised to minus 2. Okay. When you multiply, you will get the answer as, see, when you multiply, 15 into 0.5 is 7.5 into 12 into 10 raised to minus 4. And when you multiply this, 12 into 7.5, 12 into 7.5, it will be 90. So we will get 90 into 10 raised to minus 4 is 9 into 10 raised to minus 3 volt. This will be the EMF induced. So what is the magnitude? Magnitude of EMF induced is equal to 9 into 10 raised to minus 3 volt. This is the magnitude of EMF induced. Okay, so this is the magnitude of EMF induced. Clear? So we have got first part. So EMF induced from Q to P, electron flow from P to Q. The electron experiences a force in direction Q to P, that is indicated by Fe. Okay, now next second part we will see now. Is there an excess charge built up at the ends of the rod when key is open? Yes, when key is open, excess charge is positive charge at P, negative. So there's an excess charge developed. So first part I can write, when key is open, key open, excess charge, okay. Now this key is closed, what happens? When key is closed, what happens? Electrons are actually flowing in this direction. Electrons will start to flow continuously like this. Okay. So there will not be any excess charge there. Because of flow of electrons, there is no potential difference developed. There will be continuous current. So when key is closed, no excess charge. No excess charge, but current flows. So, but current flows. Okay, current flows. Because of this, there is no excess charge developed. Okay, when key is open, there is excess charge. When key is closed, the excess charge will be stopped. Excess charge, there is no excess charge developed, but there will be current flowing. Now, third part. With the K open and the rod moving uniformly, there is no net force on the electrons in the rod PQ, even though they do experience magnetic force due to explain. See, I told that there is electrons moving in the conductor in this direction. Okay, electrons are current is in this direction, electrons in this, but the conductor is moving like this. So we can say this is the direction of when conductor is moving, electrons in the conductor also move in this direction. I can say electrons move due to the movement of conductor, electrons move in this direction. Then what is the direction of current according to the movement? See, we can say there will be a current in this direction. Current is against the movement of electron. This is the direction of velocity. When conductor moves in this direction, electrons also move in direction. So accordingly, there is a current in the opposite direction. And there is a magnetic field in vertically downward direction. We need to find the force. See, electrons moving in a magnetic field experience a force. That we can understand by Fleming's which rule? Left-hand rule. According to Fleming's left-hand rule, magnetic field act vertically downwards. Okay. Current in this direction means leftward direction. What is a force? Electron experience a force due to magnetic field in this direction. This direction means from P to Q. Here P, here Q. So P to Q. So what's the direction of force? I can say FB. Due to magnetic field, the electrons experience a force FB. It is in this direction from P to Q. Okay, P to Q. What is Fe? Due to electric field, the electrons experience a force Q to P. So they are equal and opposite. Okay, they are equal, they are opposite. So what is the net force? So net force will be 0. So there is no net force. Net force is equal to 0. Because FB will be opposed by Fe. So both will be opposed. See, the electrons moving in the conductor experience both forces FB and Fe. They may be equal and opposite. So their net force will be 0. Okay, now the fourth part is what is the retarding force? We need to find the retarding force. So for finding the retarding force, we need the equation. What's the equation of force? F is equal to, we have the equation BIL. But we need current. What is current? First we will find current. Current is equal to induced EMF divided by the resistance. What is induced EMF? 9 into 10 raised to minus 3 volt. And what is the resistance? Resistance 9 milliohm. 9 into 10 raised to minus 3. They cancel. And what's the answer? 1 ampere. 1 ampere is a current. Now how will you find the force? Force is equal to BIL. B is 0.50 Tesla. And current is 1 ampere. And what is length? 15 into 10 raised to minus 2. So what is the answer? The force you will get to be 7.5 into 10 raised to, okay, 7.5 into 10 raised to minus 2. 10 raised to minus 2 Newton will be the force experience. So when key is closed, then only there will be current. So when key is closed, there will be force experienced by the conductor when it moves in the magnetic field. Okay, when it moves in a magnetic field, there will be induced current. So due to the induced current, the conductor experiences a force in this magnetic field. And the value of the force is given by F is equal to BIL. Okay, now we have the next part. We are going to see the next part. Question number E. How will you solve this? How much power is required to keep the rod moving at the same speed when key is closed? When key is closed, there will be induced current and there will be force experience. So we need to send power. Okay. So when key is closed, how will you find the power? Power, we have equation power is equal to force into velocity. And what is the force value? The force is 7.5 into 10 raised to minus 2. And what is the velocity? Velocity is 12 centimeter per second. That is 12 10 raised to minus 2. When you multiply, you will get answer 9 into 10 raised to minus 3 watt. This is the power. This is situation when key is open. Key is closed, sorry. When key is closed. Key is closed. Okay. When key is closed, this is the power. When key is open. Key open. What is the value of power? Power P is equal to 0. Okay. Why power P is equal to 0? When key is open, there is no force required, no current, no induced current. So no need of power. Okay. Now question number F. How much power is dissipated as heat? See, power dissipated as heat, we have the equation I square R. I square R. And we have seen that I. What is I? Value of I is 1 ampere. So 1 square into resistance is 9 milli. 9 into 10 raised to minus 3. How much you will get? You will get 9 into 10 raised to minus 3 watt. This will be the power developed as heat. See, both power are the same. The power which you spend in moving the conductor externally will be lost in the resistor as heat. In the closed circuit, heat will be produced corresponding to this power. This is the power which we spend externally. What is the source of this power? Source of this power is the external agency. See, source of this power will be external agency. External agency is the source of the power. External agency which move the conductor will be the source of the power. Okay. Now last part, we have one more part. What is the induced EMF in the moving rod if magnetic field is parallel to the rails? See, in the figure we have magnetic field is like this and rail is moving like this. So the rail will cut the magnetic flux. If magnetic field is parallel to the rail, see, if the magnetic field is like this, parallel to the rail, no change in flux. If it is perpendicular, there is change in flux. Here, no change in flux. So when magnetic field is parallel to the rails, see, when magnetic field is parallel, what we can say? Induced EMF will be 0. Okay. See, induced EMF will be 0 since the conductor PQ does not cut magnetic flux. Okay, magnetic flux. See, when the magnetic field is parallel, the conductor PQ does not cut any magnetic flux. So EMF induced will be no EMF will be induced, no change in flux, no EMF will be induced. Okay, so that's the situation we have here. We have a magnetic field vertically downward, and horizontally we have two rails, and on which we have placed a conductor. The conductor moves in horizontal direction, magnetic field vertical, so it will induce EMF, and we have seen the direction induced EMF. Then the electrons, due to the flow of electron, due to the current, will experience a force in two field, because there is an electric field developed as well as a magnetic field, and we have seen that both the force will be opposite direction, so net force on the electrons will be zero. Okay, then we have seen the power, then the force experienced by the conductor, and last we have seen a different situation when magnetic field is parallel to the rail. Okay, we can see how it will be parallel. See, if you make the magnetic field like this, the rail is in this direction, the conductor is in this direction, and we apply magnetic field parallel to it. B is parallel to it. Okay, this is a conductor PQ. We have the conductor Q, P, and magnetic field is parallel. It will not cut any magnetic flux, so there is no EMF induced. Okay, I hope that you have understood. Thank you.